Hi, my name is Benno Weck, and I want to present my paper that I did with the help of my collaborators, Xavier Favory, Konstantinos Drossos, and under the supervision of Xavier Serra. In the paper, we look at automated audio captioning. In this task, an audio recording is presented to a deep learning system as input, and from this input, the system produces a single sentence that describes the content of the recording. Listen to this example. For this example, we expect a caption like, "The waves are crashing onto the shore of a beach." This is definitely an exciting task, and we want more people to work on it. But how can newcomers to this task get started? Looking at the paper's existing code and datasets can leave them wondering what would be a good first step. So we decided to study something that is useful for everybody who is just starting out with audio captioning, comparing freely available resources from both the audio and the language domain in a transfer learning setting. The approach looks like this. The audio is processed by a pre-trained audio encoder model to extract the embeddings. The same happens with the words. A word embedding model transforms the language input into word embeddings. A caption generation model uses the information in both embeddings to produce the sentence. We decided to use models that have proven successful in many different tasks. As audio encoder models, we choose DCASE, YAMNet, OpenR3, and Koala. And as word embedding models, we use Word2Vec, Glove, FastText, and BERT. To assess their performance, we test all combinations of those and a few more settings. To produce the captions from the audio, we use a transformer architecture. This transformer model takes audio embeddings and word embeddings as input and predicts the next word. Since the audio embedding models are quite large, we decided to not fine-tune them and to extract fixed embeddings. Instead, we investigate if adding an inductive bias to the model helps performance. We do this by applying an adapter component that processes the audio embeddings. We compare three different adapter settings: no adapter, a simple feed-forward network with a single nonlinearity, and a multi-head attention block. We evaluate our approach on the closed-through dataset that some of you might know from the DCASE challenge, task 6. We also adopt the metric from this task, the spider score. In this dataset, each audio file is associated with 5 ground truth captions. For example, a creaky door is being opened and closed with slow motion, or a door opening and closing causes a high-pitched creak. Let's look at some results. We compare the 4 audio encoder models across all model settings when the word embeddings are fine-tuned and when they are fixed. We can see that YAMNet is the best audio encoder in our comparison. When comparing the audio embedding adapters, we see that the multi-head attention block, here shown in green, performs best. When looking at the word embedding models, we find that overall, pre-trained word embedding models are better than randomly initialized embeddings. And when they are fine-tuned, they give even better results. In our comparison, Bird is the best model, with the others close by. If you want to see more results and learn more about our audio captioning model, have a look at the paper or come to our poster. Thank you for your time.